So let's wait a bit for to start recording. I think it should do. Yeah, it's already doing. Okay, so yeah, today we're gonna learn a bit about neural networks. If I'm not mistaken, Dafa, you already know about a bit about it, right?
Yes. I watched some YouTube videos and stuff, but not
Okay.
an expert myself.
Okay.
I know how it works in general.
Okay. And Ming and Lan, do you guys have an idea or?
I also watch a YouTube video because it's one of the videos that we should watch before class for the data analytics, I think. Yeah.
Okay. Okay, but okay, so well, let's start with regression analysis. I think is if you understand this, you're gonna easily understand your networks, my opinion. So does anyone know what like regression analysis is or linear regression?
I know in general it tries to measure the correlation it between two things. That's how I mainly use it for.
And answer the correlation, but if two things have a high correlation, usually your regression analysis will be successful. And so like, let's consider two variables. Since we are with finance, let's consider here money. And here let's consider like the number of hours that you study. And so here's your future income, and here's the number of hours that you study. And usually when you collect data, you're gonna only have points. So you're gonna ask someone, hey, how many hours did you study when you were in college or university? And then the person will tell you. And then you're also gonna ask, hey, how much money are you earning right now? So then you only have dots, which will be the data points. So like for instance, person one has an income of, let's say, 2,000 euros per month. And this person studied, let's say, 10,000 hours in their whole academic life. And so they also did a master's, I would say, or even PhD. But then you want to say something about the relationship between those two things. And more precisely, you would like to know whether you can predict how much money someone will earn in the future based on the number of hours that this person studied. The way that we the way you would do this, like if you just can do this graphically, would be just draw a line here to try to grab all the points that you can possibly do, and so that you have what we call the best line or best fit. But well, mathematically speaking, it is essentially so what you're trying to predict, which here is the future income. Usually we call this the y, or the dependent variable. And then what you're using to predict what you want to predict, which in this case is the number of hours, we call it x, which is the independent variable. Independent in the sense that like you consider this as a given. So it does not depend on anything. You don't need to estimate it. You just get it from the world. And then you can use it to estimate things that depend on this variable. And you can have many variables, but in this case, we're just going to use one. So x can be like x1 up until xn. But for this example, let's just stick with x1. So linear regression is essentially always has this formula, which is y equals beta 0, which is what you guys learned in statistics as the intercept. Because at some point, like you could have like here, that someone did not study at all, but this person is still earning some money, like he still has an income. Therefore, we need to have an intercept. Otherwise, you assume that if the person did not study at all, this person will not receive any money, which is not true. It could be, but usually it's not true. So usually we need this intercept, which we call beta 0 or beta naught. So this 0 here in mathematics, we also call it naught. And then you will also have beta 1 times the variable that you are using. So in our case, is the number of hours. You could have more. So you could have other betas and other x's. But essentially what you need to think is that those betas, they are the weights. So they are the amount of importance that each variable or feature has in determining the y. So if this beta 1 is very big compared to the other betas, well, probably the x1, which in this case the number of hours, is very important to determine the number, the amount of income that you're gonna earn. Up until right now, do you guys understand everything?
Yeah,
Good.
I understand.
Yes. Yeah.
Okay, so if you don't understand anything, you can just interrupt me like straight away. Because if you don't do this, I can promise you that, like, yeah, you will get lost quite easily. But okay, so right now we have our formula, and it's quite a simple formula, as you can see here, because like you are just summing things, but this is also good. And that's why we call linear regression, because if you just do like this, like you get some weights or betas, and then you multiply them with your independent variables or the explanatory variables, so the variables that explain what you're trying to estimate. If you do like this, you will always have a straight line. And the good thing about straight lines is that you can easily extrapolate. Extrapolate means like, so here we have our data, right? Extrapolate means when you want to estimate something that is outside of your data range. So like, let's say that the maximum here is 20,000 hours. And let's say that you meet like a guy that is very, like very smart. He studies the whole day, he really likes to study. And he has studied 30,000. Well, you in your data set, so what you have for data and what you train your model with it, you have never seen 30,000. So yeah, it's a bit difficult to say, right? Because you don't really know what the impact will be by studying that much time. But if you have a linear regression, you can extrapolate. So you can say, okay, I don't know, but given my model, following the line, probably you're gonna be like here. So this is the good thing about having linear models. So when you sum things together and you have just a line, you can extrapolate easily. The problem with this is that you don't really know if it is true or not. What do I mean with this? Well, so if you have someone that studied 30,000 hours, probably this person did 2 studies or 3 studies. So this person, not necessarily this person acquired more skills that are appropriated for the job that this person is currently do, but maybe this person studied like physics, and then he studied sociology, and then he studied international business. Let's assume this. Like, not necessarily this great number of hours will make this person a good employee. Maybe this person is as good as someone that studied like 10,000 hours and just did a bachelor and a master's in international business. So maybe after a certain number of hours, you start to decrease. So then right now we don't have a line anymore, right? Right now we have like a curve. So this is the bad thing about linear regression and linear models. Like the good thing is that you can easily extrapolate and say, okay, probably this person is gonna earn this. The bad thing is that it's too simplistic. Because usually in life, When you have too much of something, it becomes bad or it becomes good. Sometimes it was not good enough and then it becomes good. So sometimes the relationship changes. With linear models, you cannot capture this. Do you guys understand this?
Yeah.
Yeah.
Okay. So now the question is, okay, now we know how to draw the line. Yeah, it's easy, just draw it, right? But the difficult part is to know what the function is. So actually what the betas are. Because you're gonna get the axis. So now you need to estimate the betas. And the betas, they need to be good so that you can have this best line or best fit line. How do we do this? Well, we have the method called ordinary least squares. So ordinary is because, like, ordinary means like normal, and it's because there are other methods to do this, and they are better and more complex. But this is the most common, the most, or even the most simple one. Least is because you want the least number or the least amount, and squares is because when you train the model or when you create this model, probably you don't know what the betas are. So when you guess betas, like let's say you say that y equals 10 plus 20 x, and here x once again is the number of hours. You just guess it, okay? You don't know, but you think, yeah, maybe it's like that. When you want to evaluate, first of all, when you start with this model here, you are not estimating the correct y, but what we call y hat. So it's like an estimation. You could call this anything you want. You can also call this f of forecast. Doesn't matter. The important thing is that you want to say, hey, this is the y, the actual y, and this is the estimated y, or the y hat. And then what you will do to know if your model is good or not is see the difference of it. Like, is the difference big or small? If it is small, yeah, then your model is good, right? If it is big, then your model is not good. The issue with this is that sometimes the y's, they can be negative. And another issue is that if you only want to make this number small, if you just do like this, well, if your y hat is smaller than your, or actually if your I hat is bigger than your y, then you're gonna have a very small number, actually a negative number. But this doesn't mean that their model is good, right? Because the difference is still very big. So what we usually do is we square it. Because when you square, it doesn't matter if the y or the y hat is the biggest one. What matters is the actual distance between these 2 points. So by squaring it, you make it like, you consider both the cases where the y hat is bigger or smaller than the actual y. So that's why we say here squares, because it's like you're gonna sum this many times. So by the way, the sum symbol in mathematics is this one, we call it sigma. And it's simply showing that you're gonna sum this many times. So here you have your y t and your yt, and this t is gonna change. So this t gonna be like, I don't know, or it doesn't need to be t, by the way, it can be I or anything like that. The importance is that when you have this thing written here down, you know that it's considering a certain thing. So like, for instance, a certain person in this case, and you're going to compare to the prediction of this certain person. So that's why we have this t here, but it could be y or anything like that. After you sum all the differences of your model, you're gonna update your weights. And so let's say you do it, and then you see that, hey, here should be 30, or you think that this should be 30. So then you do like here once again, and then you do this procedure once again. And then what you want to do is you want to minimize this function here. So we want to minimize this number here. So the squares or the error squares. Okay. If we would do this by hand, it would take a lot of time, right? Because you need to do many times the same procedure. Fortunately, and this is a good thing of linear models, is that since it's like a line, it's very simple, and since it's simple, it is easy to have a formula that already does this for you, that you already get the results. There are two formulas for this. You don't really need to learn it, but just know that there is a formula that already does this directly. So with this formula, you already get your betas by only calculating one time. And by the way, we say beta hat because it's not the real one, because you will never know what is the real one, because your data is what we call noisy. So it means that like you have some variation because of other external factors that you are not accounting for. Okay. Do you guys understand it too here?
Yes, yes.
Okay.
The y and y cap is just basically the y is the actual the result, and the y cap is the data that you have.
The estimated. The y hat is the estimated. So what you actually, so you have the y, you have the x, you want to know the betas. So what do, you estimate the y's with certain betas with the I hat, and then you're going to calculate the difference. So what you estimated and what you should have estimated, so the actuals. And
so
then
you basically want to minimize the error, and to minimize the error, you use whatever. Now you use the machine learning thing.
Yeah. So, but yeah, we're still gonna come to this, but right now we're just with this method that is very famous. And here you have the formula for it. And by the way, this is like matrix, or it's linear algebra. It's quite advanced for you guys. So don't worry about it. You don't need to remember this, because nowadays computers do this for you. But the important thing to remember is that with the linear model here that we just have, that is like very common, you have a formula that you just calculate once, and then you get the result. So you don't need to do this procedure many times, okay? But if you don't know this formula, well, you can do this procedure many times, and at some point you will get the same result, right? So keep this in mind, okay? So that we have the formula for this, but there is also a way of estimating the weights or the betas by doing this procedure of guessing numbers, calculating the errors, and then guessing numbers again based on your errors to minimize it, okay? Do you guys understand this completely?
Yes.
Okay.
Kind of.
Okay, so if okay, kind of. Is there anything that you don't understand?
No, it's just you know, the I just don't have the well, I know matrices, but then like I never really do anything with it.
You're not used. You're not used to it.
Yeah. Like I know how to calculate when you add, when you multiply matrices, but like
yeah.
How do
but
you
don't
apply
worry.
that?
Don't worry, because I mean, at some point it would be nice for you to learn it if you want to really get deep in neural networks and machine learning. But nowadays, fortunately, the computer does many things So if you just want to apply the methods, you can easily do this by only using the computer. Like for instance, we had statistics at the home, and maybe you guys remember or not, but we did linear regression, but we did on Excel. You just said, Excel, here are the data, just calculate it, and Excel did it for you. With machine learning, it's the same thing. So the computer will do everything for you, as long as you are using a model that already exists. If you want to create a new model, or if you want to be very flexible, then you need to have the knowledge. But don't worry a lot about it, because if you really need to do this, you will really, you will need to learn it. So like, I would say for now, don't worry about it. But at some point, if you really need it, so if you really need flexible models, then you will be forced to learn it anyways. So I will not go for the courses to learn it, but I will just simply wait and try to avoid it as long as possible until I really need to learn these concepts. Okay? Because sometimes what happens is like people want to learn machine learning, and then some people, they just think like, okay, first I'm going to learn all the mathematics, and then I'm going to start doing machine learning. If you choose to do this, first of all, you're going to suffer a lot. And secondly, it's very demotivating because you really don't see the connection until you start doing what you want to do. So it's better to start doing what you want to do and up until your limit. And whenever you reach your limit, you broaden your knowledge, and then you do this again. Okay? So don't worry if you don't understand the matrices or things like that. The only thing that you need to know about this linear regression is we have some data. There is a way to estimate it by doing this thing of the error. So estimate, like guess the beta's error, guess again to improve your error, and then you calculate the error, and then you do this until you cannot improve your error anymore. So you cannot minimize your error anymore. But there is another way of doing this, which is like directly. So it's one formula, one calculation, and then it's done. But this one formula, one calculation is very good, of course, because it's fast. But if your model is non-linear, so if you want to, so let's get another example. So let's get an example where here you have, once again, your income. And here you have, let's say, the amount of time that you spend in the library. Okay, so now the relationship is a bit different. Now the relationship is like this. So now you can see that, like, if you try to draw a line, you're gonna miss a lot of points. Like this will be the best line probably. So this will be our best linear regression. Like what about these points here? Those people here, those people here, and those people here. You're missing a lot, right? So then for this, you need a non-linear model. So you need to have some flexibility. The non-linear model can be any function. So you're gonna say that the y equals f, and f like means function. And then, by the way, when you have brackets in mathematics, it means that like the function that you are calculating depends on certain variables. So here you're going to depend on age. So what this actually means is that like here you have a function that could be like, for instance, beta 0 plus beta 1 age, and like this age can change. So the only thing that will change in the function is the age. The rest is fixed. So here, when you have f and brackets in mathematics, what is inside the brackets is the thing that can change. Okay? Okay. So, and this function can really be anything. So it could be like plus a beta 2, I don't know, cosine h, or and plus beta 3 h square. Like it can be anything. So like there are many possible ways of doing this. And this makes the problem very difficult because with the linear regression, yeah, you know what the function needs to be. It needs to be this sum starting with an intercept or a beta 0, and then you just have weight and then variable, weight, variable, and then you just estimate it, easy. When you have a nonlinear regression, yeah, like first of all, you need to know what mathematical tools you need to use. So cosine, sine, these are from geometry, but it could also be the natural exponent, logarithm, so many possibilities. You don't have the time nor the resources to try them out. I mean, sometimes you can try to reason. So if you try to say like, okay, probably here is a certain function, and then here becomes another function. Like sometimes people can infer those things, but usually it's very difficult. And when your data gets very big, especially when you start to have many explanatory variables, yeah, it's almost impossible for a human to do this. But now what we have is machines and machine learning and also neural networks. Fortunately, they can do this not because they are smarter than us, or not in my opinion, some people think, but more because they are faster than us in calculations. So they can really try many possibilities and see which one is the best. So with neural networks and machine learning, we are not using this one formula that gives us the answer directly, what we wish we could, but we are doing this long procedure of trying things, getting error, trying things again, getting error, and trying to minimize the error. Okay? Does anyone has any question up until here? Okay, so we're gonna continue. So right now we know what the neural network needs to do. So the neural network needs to find a function that is nice, that will feed the data nice, so that we can use this to predict things. Okay, so now there are different ways of using machine learning, by the way. Today, I'm gonna focus on neural networks because it is a very hot topic and it's also in my research area, but also there are other ways, just so that you know. But I would say that the most popular one, especially right now, are neural networks. So, okay, so neural networks, well, is essentially trying to copy the brain. So in the brain, we have some neurons, and then they are all connected with each other. So here we have two neurons, and they are connected with each other. They send some message here, and then by doing so, you can think, you can reason. So it's essentially just sending message, and then the next neuron gonna get your message, interpret, and send to the next one until something happens, maybe until your hand moves or until you have an idea. But what is important is that you have a neuron. So you have like a thing that is connected to another thing. And inside the neuron, you will have a transformation of the message or an interpretation of the message. Neural networks are the same thing, or artificial neural networks, if you want to be, if you want to speak correctly. But essentially, you're gonna have the neurons, and then you're gonna have other neurons, and then you're gonna have other neurons. So you have what we call layers. So this is the first layer, second layer, and third layer. And yeah, there is no limit. You can do as many layers as you want. If I'm not mistaken, Okay, actually, I'm sure that ChatGPT has more than 10 layers or even more than 20, but not 100% sure. And the more layers, probably the more intelligent your neural network can be, but not necessarily, because maybe your neural network gets so complex and your problem is so easy or much easier than what you need that your neural network starts to overthink, starts to create things that does not exist. But okay, so here you have the neurons, and let's say that actually let's go back to our problem here. So we want to estimate here the future income, and here we have our inputs. So let's say that our first input is the number of hours in the library. The second input is the income of the person's parents. And the third input is their age, or actually, no, okay, or the age that they started studying. Let's say like this. So let's put A of age. So here you have three inputs. You're gonna put these inputs here. So let's say someone has studied 10,000 hours. This person's parents' income is 20,000 euros per year, and they started studying when they were 18. Okay, so we have these inputs, and we just put in the neural network. So here, usually the first layer of the neural network is used to just get the inputs. Once the inputs are here, they are passed to the other layer. And they are passed to each neuron. And that's why I started with the linear regression, because inside this neuron, you could think that you have a linear regression. So inside here, you're gonna have your y, and then you're gonna have your beta 0, beta 1, and then the h, and then beta 2 income, and then beta 3, and the number of hours. And you have this for this neuron, but you have also for this neuron, and for all the neurons that you have in the second layer. So for each one, you have a linear regression, okay? Then, after you calculate the y's for each neuron, you're gonna just sum it up, everything, and then you're just gonna give to the third neuron here, or the third layer, and the value that you get here will be your estimation for the future income. So it's the same thing as the linear regression, literally the same thing up until right now. There are more complex neural networks that we're gonna see soon, but up until right now, we are just saying like, hey, instead of doing one linear regression, what about doing two? In our example here, two, but it could be more. And then you just sum up everything that you have estimated, and then you're gonna have your estimation. And then we come to that procedure that I just told you. You're just gonna get your y, so the actual minus the estimation, and you're gonna square it, because if you don't square it, you're gonna you are not measuring the distance, because sometimes it can be higher or lower. So you actually want the distance and not the number. So that's why you need to square it. And then you just want to minimize the sum of this. And you do this by simply, or the neural network will do this by estimating the wages and then calculating the error and then estimate it again and then calculating the error again and doing this until the error gets in a place that you cannot decrease it anymore. Okay. Up until right now, do you guys understand everything that I just explained about this example?
I have a question actually. Is it So the first step is the input, right?
Yeah.
And then the second step, could it be more than the number of inputs? Because it's
Yes. So yes, it is possible, and this is also nice. So actually, in theory, you could also have like this.
Yeah.
And
Okay.
also another nice thing is that you can have also multiple outputs. So you can also estimate other things. So right now we're just estimating the income level, but you can also estimate how happy this person is, and you can also
Interesting.
estimate the number of children. And like usually with linear regressions, you cannot do this. You cannot do this directly. You need to do one linear regression per time, and it costs some time, even though you already have like one formula to already get the betas. But here with this neural network, you can estimate the three at the same time, and sometimes there is some correlation between these three things. And here is a clear example, right? So if you have a lot of money, you are happier. And probably if you have a lot of money, you will not have many children. Actually, it depends on the country. Here in the Netherlands, maybe you're going to have quite some children if you're very rich. But in other countries, like in developing countries, usually it's the opposite. But anyways, the thing is, sometimes these things here, they are correlated. And usually neural networks can learn this correlation. So that's also something very nice about neural networks, is that first of all, you can have a lot of regression analysis. And by having a lot of regression or linear regressions, you can be more precise. You can learn more, more difficult patterns than just by having only regression. Okay.
And the second part, is it just one function with varied weights, or it can be different functions? And
Okay, so this is the first layer, and then your question is about the second layer, or actually between the second and the third layer?
I don't know the difference between the first and second and third, actually.
Yeah, okay. So the first, for now, first is just the inputs.
Yeah.
Second is the linear regressions or the calculations. And for the third layer, it's just summing things up. You just sum it up, and then you get your result. The second layer, for each neuron, so for each of these balls here, you have the regression, the linear regression.
Yeah.
And then you're gonna get the results, and then you just sum it up, and then you're gonna have your outputs in the third layer. So, okay, but what was your question once again?
So the neuron is just the parameter. Like, what's the why is there so many? Like, if there's many, what does it mean? Just more parameters. What's happening actually?
Yeah. So for instance here, each neuron. So we are estimating. We are using 3 inputs, right?
Yeah.
Each neuron will have 3 weights plus the intercept. So each neuron here will have 4 things that needs to be estimated.
Yeah.
And the things that the computer will estimate, we call parameters. So here we have 4 times 5, we have 20 parameters. Another nice thing about neural networks is when the neural network is summing everything to give you the output, usually you also have another thing here that will also be summed, and this is what we call the bias, which you could think is another intercept. And sometimes this works usually works very well, because sometimes the neural network is going to the good pattern, so the neural network found the good pattern, but it's always underestimating it, and then it's very easy to just sum something, and then you get the good result, because sometimes the neural network finds the good pattern, but then it's underestimated, and if you will not have this bias, you will need to estimate everything again.
Okay. So for follow up my question, like these 4 things, when you want to do this neural network machine learning thing, do you define it, or is it like
so this is a nice thing because you don't need to define anything. Like
Okay.
you have certain things that you need to define, that these are called hyperparameters. And okay, we're gonna learn about them, maybe not today, but one thing that you already know is like the number of inputs. This is a hyperparameter. Also the number of neurons that you have in the second layer, so the number of linear regressions, is also a hyperparameter. You need to decide this. And then the neural network will learn the parameters. But the hyperparameters, they are also very important. There are some rules. Sometimes you have some rules, or depending on the field, it makes sense to use certain things. For example, in finance, usually when you want to do when you want to estimate, for instance, stock returns, usually you do per week or month. So like, for instance, if you want to estimate next day's return, yeah, usually gonna use 5 inputs because this is like a business week, or 22 inputs, this is a business month, or 252, this is a business year. But for like a biology, is another thing. So it really depends on the field, these hyperparameters. But one procedure that everybody follows, and then what will come here right now, is like when you are trying to model something, you're gonna have your data, right? But you cannot train your model with the whole data and say like, hey guys, look how good I am. Because if you do this, what will probably happen is that you will overfit the data. So, okay, coming back to the linear regression example. So clearly, the best option to model this that we had for the first example is drawing the best fit line, right? But if you just if you just train your model with the whole data, and if you train enough, your model will do like this. It will connect all the points. Because if your model connects all the points, the loss is 0. But at the same time, you're not estimating anything. Because when you want to model or estimate something, you want to see the pattern. You want to find the pattern. You don't want to find the exact things. Because when you have measures or anything like that, you have some variance. And this we call, by the way, noise. So noise means like that, for instance, ideally, the number of hours that you study should always, like, if you increase the number of hours that you study, you should always earn more, ideally. But sometimes there are other factors that are important. For instance, if you get sick, well, if you get sick, you can continue studying, but if you get sick before you just need to work, yeah. Or also maybe your skin color. So in society, we have some races. So maybe even if you study a lot, you will not get a good job because society is racist. So these things that we are not modeling, we call them noise. And like, we don't want to learn them because, first of all, if you just learn it by learning it, you don't really know what they are, because they are actually a collection of things. And secondly, well, here in this problem, we are interested in the effect of the number of hours that you study and your income. We are not interested in other things like your health or your skin color or anything like that. So we don't want to model this. So what we do to not overfit is that when you get the data, you separate it. You separate it in the training set and then the test set. And then well, as it already states, the training is used as training. So you're gonna estimate your parameters with the training set, and the test will be used to test your results. So hopefully your results here in the test are very good. And also in the training set, they are also good. But hopefully they are also almost the same. If they are almost the same, it means that you probably found a pattern in the data set, and then this is what you want. If your training set has a very good result, but your test set has a very low result, yeah, probably you are doing like this. You're just connecting the dots, and then everybody can do this is easy. What we do want to know is try to predict things, and that's why we use the test set. Okay, it is what we normally do. With machine learning, we add something. So we get a part of the training set and we use it as the validation set. So coming back with the hyperparameters, yeah, I mean, how can you possibly know which hyperparameters you need to use? Like the number of inputs, or the number of neurons, or the number of layers, and the list goes on. The more complex your neural network becomes, the more hyperparameters you need to choose from. You don't know. Nobody knows. You can have some guess, you can have some intuition, but you probably don't know for sure. So what we usually do is we say, hey, let's get the training set, let's separate 10% or 20% of it. And then what we do is we train many models with different hyperparameters, and then we test them in the validation set. The best model, or the best results from the model that you get in the validation set, this model will be used for, or the hyperparameters of this model will be used for your whole training set, and then will be tested in your test set. So it is as if we did this procedure of training set and test set 2 times. But once again, we are never touching the test set. It's something very important. Don't ever touch the test set before testing. Otherwise, you are simply cheating. Because, yeah, once again, you can perfectly model anything if you have the data. But what you want to do is you want to model something to be able to predict things in the future, or to know that you really know the patterns of it, and not that you are simply overfitting it and just drawing lines between dots. Okay, so the hyperparameters, the things that you need to choose from, you usually decide this by doing many tests with validation set and then choosing the best one. It's not perfect, but right now it's the best that we have. Okay. Okay, up until right now, any other questions?
All good.
Okay. So right now, we're gonna go a step further, but the example is still the same. So we have 3 inputs. Here we have the number of neurons. Doesn't matter the number, but okay, let's put like 5. And here we have the output, let's put 1. And also we have this one here that is like the bias, because yeah, usually it helps, but if it doesn't help, yeah, then the bias is just 0. Your neural network, we're gonna learn this. So now, here the second layer, we have the linear regressions or the calculations. But now it becomes the question, okay, so first of all, the weights, they are started randomly, but usually the weights are between 0, or actually better said, they are usually between -1 and 1, usually. If not, it can be difficult, right? Because between -1 and 1, let's say you have like a lot of numbers, you have n numbers, right? But like, let's say that you don't know, you really don't know what the weights can be. Then the weights can be between -infinity and infinity. And between these, you're gonna have infinity times n possibilities. I mean, yeah, just by having infinity, you know that it won't work, right? So what we usually do with neural networks is we scale the data. So before giving the data to the neural network, we transform it by getting like the data, so the original data. So let's say the original data is 100, right? So 100 hours, okay? Instead of feeding 100, and by the way, let's say you want to predict the number of income per hour. Let's say this person is earning 13 euros per hour. Yeah, you can easily see here that you will have a problem. Or actually, let's make the contrary. So you want to, given the salary of someone, you want to predict how many hours this person studied per month during college, okay? You can easily see here that the weight here will need to be almost like 8 or 9. Only with this example, of course. But probably it could be like more than 1, or it could even be less than 1, depending on the thing. So then we get into this problem. How do we come back to this easy solution? We normalize the data. Normalize means that like your data will be between 0 and 1. Like for sure, your data going to be between 0 or 1, no matter what. There are many ways of normalizing data, and I can even show you here. So yeah, there's even a whole Wikipedia page about it. Okay, not this one. Okay, this one is nice because here you have some some examples. There are many ways to normalize the data. The most simple one is this one, min max future scaling. It's easy. It seems difficult, but it's not that difficult. So the formula here is showing like that you have your new data, and your new data is going to be the old data minus the minimum of the old data divided by the difference between the maximum of the old data and the minimum of the old data. I mean, yeah, I could mathematically prove to you guys that your result will always be between 0 and 1. But for now, you can just believe me that this is the case, that like no matter what, this will give you a result between 0 and 1. Okay, so do you guys understand this concept of normalization? No questions then, right? Okay, so once we have done it, we can start our guess for the weights in a much safer way, because now we can there's a limited number of weights that you can possibly generate, and then you're gonna do the calculations, and then you're gonna get a result, and then you're gonna get your error. The error we usually write like this E actually is a Greek E, it's called epsilon. And with time, you want to decrease the error. Okay, how do you do this? There is a mathematical way of doing this. It is impossible for me to explain to you guys without you guys having a lot of knowledge about it. But the name is important for you guys to know. Is called gradient descent. Okay, it doesn't really matter the mathematical, or for now, it doesn't really matter how it actually occurs in the mathematical way, but let's have a look how it occurs graphically. Because this you guys can understand. And Okay, so this one is a nice one. So here we have two parameters, or okay, let's think like this first one is the weight. So sorry, the intercept, and the second one is the weight that you are giving to your x variable, to your explanatory variable. Okay. And this is what we call the cost, which is another way of saying the error. So cost, error, these two words are like negative words, so you usually want to minimize it. Depending on the numbers that you choose, you will have a certain cost. So here you're seeing that if you choose 6 for the intercept and -6 for the weight or the beta, the first beta, you're going to have a high cost. And then, but if you choose between, like, for instance, here 0 and let's say -2, you're going to have the lowest cost, so the B here. What your computer does and what mathematically happens is that when you are first, you start with your guess, and let's say we are here with A, then your computer will do some calculations to know which direction you should go. So in this case, the direction that you need to go here with A is like this, right? Going down. But if, for instance, if you are here, you also goes down, but you go down like by going another direction. So instead of going like down in the sense of like going to the right a bit, you are going down, going to the left, more or less. So it depends on your placement. But to know this direction, your computer does something called gradient descent. Yeah, descent means like to go down, descent. And gradient, it is what it uses to estimate the direction. It's a bit complicated how to know the direction, how to calculate it. But I think graphically, you guys can see how it happens. So essentially, your computer will estimate, and then it will go down a bit, and then it will try the new weights. And then it will go down a bit, try new weights. Go down a bit, try new weights, until it reaches here. When it reaches here, it cannot go down further. So then it stops, and it says, hey, this is the best one that I found. As you can see, it is very low, but it's still not 0, which is normal. So don't expect your neural network to be perfect. No, it will find the best possible estimation, but it will not be perfect. Okay, do you guys understand this?
Kind of.
Kind of. Okay, so what do you not understand though? Like, okay, and yeah, the procedure, mathematical procedure behind it, yeah, this we will not learn, but graphically. So look at the image.
Oh yeah. I mean, this is matrix, vector, and all that stuff, right?
Yeah. It's a calculus and other things. But yeah, don't worry about the mathematics.
What's a color actually means, like the
Yeah, so the color here is just showing that the closer to red, the higher the cost. The closer to blue, the lower the cost. It's just to make the visualization easier.
Okay. So, and then also like, let's say for this example, maybe you don't know, but like, what is the x, well, there's no x-axis, but like the bottom axis?
Yeah, so that's a good question. So yeah, usually in mathematics, we have the x-axis. So here we have y. And then we have the x-axis, right?
Yeah.
But here, what we are seeing is that we also have the z-axis. And then you have here your estimation, so your thing. So here the y is showing the cost, the z is a direction, and the x is another direction. But you can have more directions than this, because here we are just considered two parameters, right? So we're considering the parameter z and the parameter x. Well, remember I told you just now that here we had 21. So 20 plus this one, we had 21 parameters. Yeah, you cannot draw a graph with 21 directions, but your computer and the mathematics behind it can do this procedure. So here we are just seeing a single procedure with 2 parameters, but you can do this with many parameters, but then you cannot see anymore. But the mathematics is still work. The only thing is that you cannot visualize it.
Okay, interesting. Thank you.
The important thing is that, like, probably you're just thinking, okay, so let me see. By the way, if I can copy this and put here and draw, because then it's easier. Yeah, I can. Nice. One moment. I'm just gonna. So you're probably asking yourself, why do we need to do this procedure? If, like, by looking at the image, we can clearly see that, like, if you know the direction, and like by doing this thing mathematically, you know the direction where you need to go. Why do we not simply go directly from A to B? Why not doing like this directly? A, B, one thing, done. The problem is that, like, sometimes, okay, so you're gonna get the direction, but then you still need to estimate your step size. So how far you will go. This is difficult to estimate. You cannot know in advance. And if you are very close to B and you put a big step size, what you will do like this, and then it will come here. So you will pass through B, but your step size was too long, and then it just came up again. And then if your step size is too big, it will, yeah, you will stay doing this forever and never reach B. But if
what do
your
you mean by too big?
Yeah, so for instance, because the calculation that the computer does and that you can do mathematically, we only tell you the direction. So here the direction is like this, right? But now comes the question, how much should I go into this direction? Like, should I go a lot and, like, for instance, change my, so let's say my weights here. So here A, the weight, or so B0 is 6 and B1 is -6, right? So here we see 6 and -6, and this is 8, right? And the direction here is telling us, hey, B1 needs to increase and B0 needs to decrease. This is what you are learning. So we are, okay, now we know one needs to increase, the other needs to decrease. And then comes the question, how much? Because if you just say, like, okay, let's increase, or let's decrease B0 by 10, so it's going to be -4, and let's increase B1 by 10, so it's going to be 4. Okay, if you do this, then what will happen to you is that here you are A, right? And then you said, okay, let's go to -4 for B0, so here -4 is here, and then 4 for B1, so then you are here. But you went to the good direction, so you were going towards B, but your step size was too big, so you went to B, you passed B, and you continue, and then you came here. And then when we are here, you're going to estimate again, and we'll tell you, hey, B4 needs to increase, B0 needs to increase, and B1 needs to decrease. And then do the same procedure, and then you come back to A. So, because, like, the thing that, like, the computer will know the direction, but it is impossible, like literally impossible, to know how, like, the magnitude, how far you should go. So how far, or the amount that you need to change the weights. You know where you should change the weights, but you don't know how much.
And to know why, you need to understand the mathematics behind it, or
to understand the direction, you mean?
Like why the computer cannot figure that out.
Yeah, then you need to understand the direction. Sorry, not direction. You need to understand mathematics, but essentially it is because you are when you're doing this procedure, you are dividing B0 by the cost. But by the way, not the number, but rather the mathematical structure, which we call the function. When you do this, you're gonna get a number which is like a normalized number. So it's not the actual number, but it's the number after passing through the cost. So like it doesn't really tell you, like it tells you the direction. So if this is positive or negative, then you know if it's up or down. Or you can also tell you, for instance, so let's say that here we have X and Z. So like the X and Z here are like the directions, right? And it gives you like 3 and 0.5. So then here you know, okay, you need to go more towards 3 and a bit towards Z. But not necessarily this will lead you to the lowest cost. It just gives you our direction.
So it will not tell you like the end point. It will only tell you if it's up and or down, something like that.
Yeah. Okay. It just tells you the direction, and it tells how important certain directions are. So in this example, 3 is much more important than Z.
Why?
It's just an example.
Okay.
Okay, but in this example, it's because 3 is bigger than 0.5. Okay, so we have now this issue. So right now we have estimated the weights, right? We started and then we get the error, and then we have like this graph here. And right now, and by the way, you don't know where you are in the graph. It would be nice to know, but you don't really know. The only thing that you know is where you need to go to. So right now we know where we need to go to, and now we need to estimate how far we need to go. If you estimate too big, then you're gonna do what I just said, that you're gonna pass through B, but then you're gonna go to another point that is also bad. So if it is too big, you're never gonna reach B. You're always gonna pass through it, but never stay there. So then you can just think like, okay, let's do very small, right? Because if you do very small, then you go like this, and then at some point you're gonna be around B, like you're gonna be good enough. Good, like it's a good way of thinking. But if you do very small, your computer will need to estimate the weights many times. And then it will take too long for it to calculate it. So we have this problem, like if you did, and by the way, we call this, so how far you go, we call this learning rate. So if the learning rate is very high, time goes down, but accuracy also goes down. If the learning rate is very slow, time goes up, accuracy goes up. Okay? So you have a trade-off. Usually, the neural networks that you have online, they already have a nice learning rate that works well for almost all problems. So usually you don't need to worry about it. But it's nice that you know that this exists. Okay? Any questions here?
No.
Okay, so now just a question, just out of curiosity. There is a way to do this. There is a better way of doing this, like regarding the learning rate. So instead of choosing between a very big or a very small one, or like a random number, there is a better way of doing this. Do you guys know what the way, or can you guys think of any way that perhaps you guys will try?
I don't know, just randomize it?
No, okay, you can randomize in the beginning to get a number, but the smartest way, and we already have this nowadays, and it's after you hear it, it becomes very obvious, is that like we start with a high learning rate, and with time we decrease the learning rate. So because if you are here in the beginning, yeah, you can take big steps, right? You can go like this. But if you are here very close to B, you cannot take big steps. You need to take smaller steps. So you start with a very big one, and with time you decrease, because with time you're probably approaching B. So this is a clever way of dealing with this problem. And also many neural networks that you have online that you can guys use this. So you start with a big one, take big steps, and start to take smaller steps until you reach B. Do you guys understand this concept? Or any questions about it? Okay. Okay, so now we know how to, we know more or less how the neural network works. So just some calculations, output, linear regression, not that difficult. We know how we can deal with big data in the sense of like the number is much bigger than what you're trying to estimate something that's much bigger than your input. And this can create an issue with estimating the weights. And by the way, okay, to solve this, you have something called normalization. And you don't need to remember this formula because all the neural networks that we have this formula. But just one graphical representation of normalization. So we have this graph, right? Without normalization, we would start here in A, or we have the chance of starting in A. If you normalize the data, you will start below this line here that I just drew. So you will start here, for instance, like for sure. So it makes the learning faster. And then when you want to come back, and then you're going to estimate also something that is between 0 and 1. And then to come back to the original estimation, you just use this formula once again, but you invert the terms. But yeah, your computer does this automatically. But this is the nice thing about normalization, is that like you don't have like a, yeah, this graph here is not that big just because you normalize it. That's easier. And then you have and then we just learned how the neural network actually learns, which is essentially trying to decrease the weights, and it does so by using gradient descent, so by going from A to B. And yeah, you should not take big steps, and the steps are called learning rate. If you take 2 big steps, you're never going to reach B. If you take 2 small steps, you're going to reach B after a long time. So it's better to have a nice number, or what I just said is you start with big steps and you start decreasing to smaller and smaller steps. Okay. Okay. So up until here, any questions? Okay. So now, once again, the same example. Here, 3 inputs for the first layer, and then 5 inputs for the second layer, and then 1 input for the third layer, or actually the output. Now, so in the beginning of the lecture, I just told you guys about the linear regression and like how linear functions are nice to extrapolate, but how they are bad regarding modeling difficult things, like for instance this. So yeah, you cannot model this well. So let's say that this is once again your future income, and here's the number of time that you're spending in the library. And then, but if up until right now, we just said that in the second layer, you have the linear regressions. And I told you guys, and it is in the name, linear regressions are linear. And I told you guys that linear regressions are linear because, well, it produces a line. And the second thing that you know that it will produce a line is because it has this structure here. So it has the intercept, the weights times the explanatory variables, and you just sum everything. So you will have a line. But using this knowledge and using this reason, you can say the same about the neural network. Because if the neural network always have linear regressions here, and you just sum all the linear regressions up, you will also have a line. And this is true. So up until right now, with the examples that I gave with linear networks, doesn't matter how much you train it, how well you train it, how much data you give it, you will get a line. No matter what, you will get a line. So how can we make this more flexible? How can we make it this non-linear? We do this by the so-called activation function, or functions, because there are many possible activation functions. So the activation functions, they are usually between the layers. So they are like here or here. They usually are strange or crazy functions. Like one of the most used functions in here is what we call the sigmoid function. And its value is like this. So here you have the value that you're gonna get if you put the thing, like the input. So it goes from here, and then it goes like this, and then it goes like this. And the maximum here is 1, and the minimum here is -1. Or you can also modify this function to give you only 0 and 1. But the thing that you really need to remember is that this function is a bit crazy. It's not a line, it's a curve. Same thing with like here. We have also this function, it's called ReLU. It's quite famously used, and ReLU. So it is 0 until a point, and then it goes like it becomes a straight line. And you could say that this is a straight line, of course, but it's only a straight line after a certain point, because here you have like an angle, so it's not really a line, and it's actually like bended, and this we consider also a curve. These activation functions are there to allow the neural network to perform nonlinear estimations. How it does, for now it doesn't matter. You can learn this mathematically, but for now you don't really need to, and you don't need to know this to use the neural networks. But what you need to know is that they are there. They are usually here and here, or in between other layers, and they will allow your neural network to learn nonlinear patterns. Nonlinear patterns are here like the curves, or for instance, seasonality, something that we have a lot in finance, is a nonlinear pattern because you cannot draw a line, right? You need the curves. So this is something important. And this we use a lot in finance because, like, for instance, if you want to estimate, if you want to forecast your demand, like if you're selling ice cream, here is summer, here is winter. And you want your neural network to learn this. If you use a regression analysis to do this forecast, you will get bad forecasts. If you use neural networks with these activation functions, you will get good results. You will probably get such a graph, such estimation. So once again, so we have the first layer inputs, and then you're going to have an activation function that will change the number a bit. Second layer, the calculations, usually regression analysis or linear regression. And then between the second and third layer, you have another activation function. And then third layer, you get your output. Any questions about the activation functions? Okay. So right now we're very far, right? So, I mean, right now we are almost, I mean, you can go further and create new networks and things like that. But right now you guys have everything that you need for a good neural network. So let me just check if I'm forgetting anything. I'm just gonna have a look at one of the neural networks that I created. This research that I did about predicting realized volatility of the S&P 500, and I created a neural network. But it's essentially the same. Okay, you need to understand Python, but Python is just a language, so you're just applying everything that I told you up to right now. So like for instance, here you have this scalar, and scalar is what we learned about normalization. So it's essentially transforming the inputs into 0 and 1s. Then you have here the number of inputs, number of neurons, epochs. This I did not talk about it, but let's have a look at it once again. So okay, so coming back to here, how the neural network learns. So once again, you started your weights, and then you did your calculations, and then you get the error. And the error is like here. So we are here in A, and then you want to move to B. But now comes the question. How many times should you estimate the weights, calculate the error, and move towards B? This question is important because if you train your neural network too many times, it will probably go to B and will stay there. But first of all, it will reach B and it will continue training, and we will not learn anything new, but it will continue training, so it will cost you time. So this is something that we want to avoid. But at the same time, if you don't train enough, it will not reach B. So you want to train enough, but not too much to not waste time. And another problem of training too long is that you start to overfit. So as I told you here, so here you have the data, right? And I told you, hey, you can just draw the lines between the dots and you will get the perfect model for this trainer set, but it will probably not be good for the test set. So it will be very good for the data set, but it did not really learn the patterns. It just learned how to match the things and not have any error. But this is not what we want. And with neural networks, this can also happen. So this is something that maybe is a bit strange, but if you think well, it is not that strange. So once again to this graph. So here we have the graph, right? Here we have the cost and the two parameters here. So here is beta 0, here's beta 1. You would think like, okay, if I go to B, I'm good. And that's what I just told you guys right now. But this is not entirely true. Why? Because if you go to B, and let's say that B here equals 0, then you're gonna have like something like this that I just drew to you. So you're just gonna have like a perfect model, but it's a perfect model for a training set. So you did not really learn the patterns, you just learn how to connect the dots. And this will be bad for your test set. So this can sound a bit counterintuitive, but actually we don't want to go to, like, we are going towards B, but B is not the best position that you can stop your training. Maybe the best position, it is here at C. Why? Because the most important thing of your model is to perform well in this test set. And here we are looking at the graph of the training set. Usually, if you have good results in the training set, you will have good results in the test set. But if you go too much, you're gonna overfit. So we want to go to C, but you don't know where C is. That's the first thing. You know that it's close to B, but you don't know where it is. The only thing that you know it is where B is, because B is the lowest point. B is equal to 0. So once again, we do the same procedure. We train the neural network. We estimate where you should go to. So you should go towards B. So you get the direction. You use the learning rate to know the step, like how far you should go in the graph. But at some point, we want to stop here at C. So we don't want to pass C, but also we don't want to stay here very far away from C. So C is the perfect thing. And there's where epochs are very important. Because once again, if you train not enough, you will be far from C. If you train too much, it will cost you time. And secondly, it will cost you time. And secondly, it will overfit. It will not do well in the test set. So it needs to be not too many epochs or not too few epochs. And once again, epochs is simply the number of training sessions that a neural network has. Once again, this is a hyperparameter. So you don't know in advance. It is impossible to know. You can have an idea, but find it difficult. Maybe after some years, I still don't have this idea. And so what you should do is what I told you guys about the validation set, using the validation set and just trying different epochs and then seeing how it goes. I mean, of course, you know, like you don't know the exact number of epochs, but you know there will not be 100,000. So like here, the ones that I considered are 3, 5, 10, and 15, because I know that, like, given the number of data that I have, it will not probably be more than 15. And also this task, okay, this task is difficult, but at the same time, it is very difficult to even know if this task is possible, like if you can really model the realized volatility. And if you train a lot, you're probably gonna just model the noise that we are not considering. Okay, so does everybody understand epochs right now?
Not really, to be honest.
Okay. So you understand that the epochs are like the training sessions, right?
Yeah.
Okay. And you understand why it will not be good to have too few epochs, right? Because then you are not. And if you
just automation, right?
Just what?
Automation.
What do you mean automation?
Okay, like then I don't understand what does the number means, like that 3, 5, 10, 15.
Okay, yeah, it's simply the number of training times.
Okay.
Yeah. So 3 means like that the process that we are just discussing about estimating the weights, calculating the direction to be, and moving. The neural network will do this procedure 3 times.
Okay.
So you start here at A, go here, do again, go here, do again, and stop here.
Is this the learning rate? Means like if low epochs mean lower learning rate, or is that a different thing?
Yeah, they are different things, but at the same time they are very related to each other. Because, okay, so the epochs is the number of times that you move, and the learning rate is how much you move.
Okay.
So if you choose like a lower if you want to move not a lot, you're gonna need more epochs, right?
Okay.
But if you choose to move a lot, you're gonna need less epochs. Because if you choose too many epochs, you're probably gonna miss B, and vice versa. So the epochs, the number of epochs, or the number of training sessions, you can name it like that, and the learning rate, they are related to each other. Okay. But about the explanation that I gave about C, that actually B is not the best point to be, but rather C. Do you guys understand this?
Yeah.
Yeah, you do. And you, Lan?
Not really.
Okay. Okay, so you understand that like there is a possibility that you overfit your module, like your model, right?
Yeah.
So like yeah, that you just connect the dots and you don't learn anything useful.
Yeah.
Okay, so this is important. So B is when the error equals 0.
Yeah.
Do you remember that I said about noise?
Yeah. Yes.
Yeah, so we know that there is noise. So we know that there are some things that we're not taking into account that will make some variation. If we know this, like we are sure that there's some noise, yeah, we can also be sure that your error should not be 0. Because if your error is 0, but you're explaining something complex with one variable, yeah, then you are overfitting for sure. Because it is impossible to explain for your future income just by the number of hours that you studied. Like there are many other things that are important. So if you know that you are explaining it very well, like you have 0 error, yeah, that you are probably overfitting. Not probably, you are overfitting.
Yeah. Okay.
So even though B seems the best because like the lowest error, it is not the best one. It means that you are overfitting. So it is between, like we know that the best point is between A and B. It needs to be between A and B, and it should be closer to B than to A, because A is like the worst one, B is the best one. So it should be close to B, but it should not be B, because if it is B, you are sure they are overfitting. So that's why we want to stop close to B, but not very close to B. We want to stop here at C.
Oh yeah.
The good thing is that
makes sense now.
Yeah. And the good thing is that C and B, they are usually in the same direction. And by the way, you could have many possible C's, huh? You could have, so not necessarily, like you can have like 2 models that are as good as each other, but they just model the thing differently. This is totally possible. And like it's just here that you have C1 and C2. They are both as good. So it doesn't matter where you are, the direction that you will get with your calculations will lead you towards B, but it will also lead you towards C. So actually, you can think of C not as a point, but like as a here will be like a circle or a plane or area. Do you guys understand this then?
Yes. No.
Okay. So, well, we are now very advanced, right? Now we're gonna add one other thing, but yeah, let's just re-see everything. So you have the inputs, you have the calculations, the linear regressions, and you have the output, and you normalize your data. So it's like between 0 and 1. And here, once again, you're gonna get an input between 0 and 1, and you just renormalize it, you just do the inverse, and then you're gonna get your actual prediction. And then also between the layers, we have the activation functions. Let's just call g of x, but you can call whatever you want. It's just an activation function, and this will help us to learn nonlinear patterns. And then you have the number of epochs, which is the number of times that you're gonna train your data, and the learning rate, which is the size of the steps that you're gonna take towards B. And they are related to each other, but they are not the same. And now, one thing that is also like, you will not think about it, but after I will tell you, it will make sense, is that when you're training your data, sometimes you will probably overfit it. Like, it is almost impossible to not overfit it, because like, even like the epochs, they are like numbers that are like 1, 2, 3, 4, and so on. Imagine that the perfect epoch for you would be 3.5. Yeah, I know. Like, because if it's 3, it is not good enough. If it is 4, it is overfitting. So like, what should we do now? To solve this problem, we created something that is very smart, but it's a bit strange, but you will understand afterwards, which is like, you train your data, but each time that you train your data to estimate the output, you will only consider some neurons. So in this case, we are only considering the red neurons, and we will only sum their estimation. We will not consider the black ones. By doing this, as you may already imagine, you can get to this number 3.5. Because if you train the neural network 4 times, and then in the first epoch you do this, so you just consider this 3, and you only update this 3. And then the next epoch, you only consider the black ones, and you only update the black ones, you will, for each neuron, you will have 3.5. So it will be as if you trained 3 times and then 1/2 time.
Can you explain this? I don't really understand. Oh, when you say black ones, so what do you mean by that?
Yeah, so here we have the neurons, right? I painted some in red, and you see the lines here, right? So the red ones, so let's say we are in epoch 3, okay? So up until right now, we just did the training as we learned, right? And now we are in epoch 3, so in the training 3. And right now, instead of considering these 2, or instead of considering all neurons, we will only consider the ones in red, and we will only sum their outputs to get the output. So we only consider them, and we forget about these 2. If you forget about these 2, then you will update only these 3, and the other 2 you will not update, like their parameters, their weights. So then you will improve them, but the other ones you don't improve. And then for the next epoch, so epoch 4, you will do the same thing, you will train, but now you will not consider the red ones. We just consider the input of the black ones. So these 2 here, that they were not considered before. Now they are considered, and their parameters will be updated, but the parameters of the red ones that for the epoch 4 you did not consider, you will not update it. If you do this, instead of training each neuron 4 times, you're gonna train each neuron 3 times. So 3 here and 3 here. But overall, you train your neural network 4 times. And this, it sounds a bit strange, but this makes your neural network not overfit because you're not training too many times your neurons, but at the same time, it improves the what can I call the accuracy of a neural network.
And this is decided by the model, like you don't.
Yeah, so then it's the hyperparameter. It's another hyperparameter.
Okay.
So here I started. So I said or will be 0, or will be 0.2, and here 0.2 means that like 20% of our neurons will be shut down. So every time that we train, we're gonna calculate everything, but we only consider, so 20% of the total neurons will not be considered for this training session. Next training session, other 20% will not be considered, and we do this every training session.
Interesting.
And this is for 0.4. Let's see graphically how this works. Because, okay, I explained, but I think with the graph will make sense. Okay, so we are here, right? Okay, if it was perfect, by the way, and it is also something that is important. So I told you that your computer knows the direction towards B, right? It's not 100% true. Actually, your computer knows more or less how to go to B, so the direction to B, but it's not perfect. So what sometimes happens is that your computer, let's say your computer is in the training, and then your computer goes like this, and then like this, and then it goes like here. Okay, so you are here, right? And you want to go to C, which is here. So you are here, and you want to go to C, okay? No, actually, to make things better, once again, C is here, and you are here, okay? You are here. Okay, like if you're looking at this, it's very easy to go to C, right? But your computer will not give you a perfect direction. So what can happen is that you go like this. Like you're still going towards B, more or less, but it just missed C. But if you look at the graph, so this point and this point, so they are here, and so okay, so here, so let's say that here is 1, and here is like -2. So you were in 1 and -2, okay? And C is in 1 and -1. If you pay attention, you're gonna see that like the 1 here is already good. Like you already are in the good spot for this first term here. But then this one you're still missing. If you train your neural network again, what will probably happen is that this 1 and -2 will become 0 and -1, probably. But look, we're so close. Like actually, yeah, if only this number would stay the same, we would be in C, would be in the good spot. So with the dropout, what the dropout does is that you're gonna say like, the dropout, we're gonna say like, okay, let's maintain this one the same, and let's just explore the -2. And when you explore the -2, you're gonna get 1, or sorry, -1. You understand this? Oh. Okay, ask them.
No, no, never mind.
Well, wait, do you understand or no?
Yeah, kind of.
Kind of. Okay. Okay. So like, is there anything that like you know that you
Can
don't
you just
understand?
give me like a summary of what you said?
Yeah. Okay. Let's start once again.
Just like summary quick.
Yeah.
Not bad.
So once again, we are here in the graph, right? And we are here in our last epoch. And here is where we want to go, right? So right now, we are just considering one neural network with 2 neurons and 1 output. So it's this neural network, okay? So right now, then let's say that you have 1 parameter per neuron, okay? So 1 parameter here, 1 parameter here. Okay, so C, which is the best one, the first parameter here, so the first neuron, should be 1, and the second one should be -1. So this is the perfect one that we want. Right now, after the 3rd training session, the 3rd epoch, you are at 1, and here you are at -2. So ideally, you're just gonna move the -2, right? And by the way, the B here is 0 and 0, okay? So the B is the perfect one, but it's the perfect in your training set. But it means that it will overfit. So it's not good. It is too good to be true, so to speak. So you are here, right? And you want to stop at C. But if you train your neural network, it doesn't really know where C is. It knows more or less where B is. And it will always go towards B. Even if it passes C, doesn't matter, it will go towards B. But this, you want to go close to B, but not very close. So if you're gonna train your neural network once again, you will go towards 0 and 0. So let's say that your learning rate is 1 here. So then 1 going towards 0, yeah, that is gonna be 0. And -1, -2 going towards 0 is -1. So this is your 3rd epoch, right? And this is your 4th epoch. Okay, so this is without the dropout, okay? With the dropout, we are in the same situation, okay? So we are here 1, -2. We actually want to go to C, but we don't know where C is. We have an idea. And so we wouldn't want to go too close to B, but close to B, yeah, would be nice, so close to C. With the dropout, let's say the dropout here is 0.5, which means that like the half of all your neurons are going to be trained and updated, and the other half will not be considered at all, okay? If this is the case, and let's say we are lucky, because it can also be unlucky, yeah? But let's say we are lucky. If we are lucky, it will not train the first thing, but it will train the second thing. So you'll not train this first neuron here, but it will train the second neuron. And then you are in your nice spot, because then you are C. But it can also be unlucky, yeah? So it can also happen that you're gonna end up like here. It is possible, because yeah, it is random. Like you randomly select some neurons and they are not trained and also not updated. So then you could ask me like, okay, Hugo, yeah, probably it's not worthwhile, right? Because it can be good, but it also can be bad. But if you do this many times, so when you train the epochs many times, usually it is better. Usually. So usually it is worthwhile using the dropout. Not always though, and that's why in my research, I also gave the possibility of not using any dropout at all. And if I'm not mistaken, with this model, by the way, this is like the validation set that I was using. So I think I can show you. Here's still validation. And after training everything, okay, so this had a dropout, but sometimes it doesn't have. And I have already done research with neural networks that did not require any dropout. That if you had a dropout, you get worse results. So it depends. But usually dropouts are good. Okay. Do you guys understand this?
Yes.
Okay. The losses. So, okay, once again, I told you, hey guys, there is this error function. So this error that we want to minimize, and which is essentially the difference between the estimate or the true thing that we want to estimate and the estimated value. And you want to square it because you care about the distance. Don't care about the sign or the number, no, the distance. So you want this to be 0, not necessarily -1 billion. Because if you say like to a computer, minimize this function or this number, for the computer, it means that the number needs to go down. But down in the sense of like it can become negative, and if it is the case, it will continue going negative. But as you can see here, you want to go to 0, so that's why you square it. Okay. But this is not the only possibility. You can also, instead of squaring it, you can also use the absolute value. So like you're gonna get a number here, and if this number is negative, just transform it to positive. And if it's positive, it will continue being positive. This is the absolute error, and this is the squared error. There are also other errors, like for instance, here, there's this error called Huber loss, which accounts for outliers. So do you guys know what outliers are? I think so, right?
No, I don't know.
Okay, no worries.
But
so
maybe I forget about it, maybe.
Yeah, no. So the thing is, so you were studying the number of hours studied and the future income, and then you have some data here, right? Okay, so then like, look, it seems quite easy, right? But maybe you have an outlier. Outlier means something that is like outside of the reality of the normal data. So here is someone that won in the lottery. Or someone that lied. Or it can be many things. Someone that, like the son of Elon Musk, something like that. If you don't account for this, like let's play with the linear regression, okay? The linear regression, the best one we know is this one, that it goes like this, right? But if you have this point here, you will simply minimize the errors. So your estimated linear regression is going to be like here. Because then you are minimizing this error and the other errors. So like it's very clear that this is not the case, and then we should simply ignore the outlier, right? Because we don't care about the outliers, because you're never going to be able to predict outliers, because there are things that, like, I don't know, someone earned in the lottery or something like that, and you don't care about this. You care about what most people, or like what actually happens. To, for instance, in this case, to really know if like studying more will make you earn more money, or if this is actually true. So this is the problem with outliers. And the same thing happens with neural networks. So you have an outlier, a neural network, it will be bad. So this hub Huber loss is a way. I will not spend time here because it will take some time to explain, but it is a way to account for these outliers. It's not perfect. And by the way, right now I'm doing research about improving this loss function. And so it's still not perfect, but it is already good enough. So yeah. So for instance, for another research that I did, I also did test another neural network, a new one in forecasting realized volatility. And one thing that we had, like I was looking at NASDAQ, and in 2000 we had the .com bubble. So like the many companies in NASDAQ that were related to internet, they bankrupted or their stock values decreased a lot. But usually this does not happen, right? It was a big crisis for NASDAQ back then, but usually this does not happen. And I don't care about this because I don't want to model this. I want to model what usually happens. And if something crazy happens, another example is COVID. So yeah, I also had once I was doing also research and I had a problem with COVID because COVID happened, can happen in the future. But usually when you are doing a model to, I don't know, and know what is important to know for inflation, you don't want to consider COVID, right? Because this never happens. And you actually never know if it will happen once again, probably will, but it's difficult to know when and how long it will occur. So outliers are not good. And that's why we have this loss called the Huber loss. And there are many other possible losses, but this is also a hyperparameter. Okay. And any questions about losses? Okay. Well, okay, bet size. This is important. So let's once again the same neural network that we're using this class, right? And then you have something called bet size. So bet size, it is like this. So if your bet size equals to 1, you're gonna feed here the inputs for one person, calculate everything, calculate the error, and update the parameters. And then you will do this for the second person, third person, until you get to, like, let's say we have 1,000 people. So you're gonna do this 1,000 times, and this will correspond to one training session or one epoch. And then you do the same and the same and the same. But if your bet size is 2, then this number becomes 500. So you do the calculations 500, and then you will update the parameters, and this is going to be one epoch. If this number is 500, then you're going to do this 2 times, and this is going to be one epoch. The higher the epoch, the faster your training, or the faster your epoch will be. But if you put everything together and you just sum things up, usually becomes less accurate. So usually what we do is we say your bet size should not be bigger than 32. If it is 1, nice, it will cost some time, but if you don't care about it, just do it. But usually up until 32, you will not lose much. Your model will not lose much of its accuracy. Okay. So do you guys understand this bet size?
Sort of.
So yeah, how else can I explain it? Okay, I don't really see any other way to explain it. So you guys can have a look at it later on YouTube about that size. But the important thing is to know that like the higher the faster, but we have a more or less an agreement that it should not be higher than 32. Like in the literature and academia and also companies, they never use more than 32. Okay. This one is also important, optimizer. Optimizer is essentially the mathematical tool that you will use to know the direction, to estimate here the direction. There are many possible ones. The best one, like usually the best one that almost everybody uses, is this one, Adam. So also will not worry a lot about it because it's quite standard to use this Adam. But just know that it's like a way that you use to know the direction that you should go in the graph. But yeah, I would just stick with Adam, and usually is the best one. Okay. Another important thing. So here, once again, we started in the A point, right? But I told you guys that when you start your training, you don't know your weights, so you just guess random weights within an interval. Better to be between -1 and 1. Okay. This means that if you guess it, if it is random in the beginning, you will not always start here at A. You could start here at C, or even here at D. And then you start your training and everything is the same. The only thing that changes is where you start. As you can already imagine, this can be important to know how accurate your results will be. Because if you start in A, or if you start in D, depending on the number of epochs and things like that, maybe with A, you're gonna reach a good point, and with D, you're gonna overfit. So it is important to notice that when you're using neural networks, okay, let's restart. When you are using linear regression, you will always have the same result. So you calculate the beta, you will get the betas that you estimated, and you get your best model. This is it. With neural networks, even if you know everything, like you know the good hyperparameters and you are sure about everything, if you train your model today, and if you train your model next week or even 1 minute after, you will get different results. This is something that is a bit bad about neural networks. There is some variability. So sometimes you can get like good results, and then you can get bad results. And that's why in my research, for instance, when I was analyzing the models, I performed the estimation and calculated the accuracy and things like that. I did this 15 times. Okay, actually in this case it was 10, but in other research I did 15 times. And then you just get the average, you get the standard deviation, so that you can compare to neural networks. This is important because you can see that like here, I could say like, hey, I got these results, or I got these results. And the difference is almost 1%. And you can think like, yeah, 1% is nothing. But regarding these tasks here that we are talking about, 1% can mean like a company earning 1 billion euros or losing 1 billion euros. So 1% is important, and that's why if you're comparing to neural networks, it is important to try sometimes and then get the average and then compare to neural networks. Okay. Do you guys understand this concept of randomness? Okay. Regarding the basics, I think we covered everything. Two things then. First of all, yeah, to implement it, you need to learn Python. But at the same time, you can copy and paste many things. And if you don't know something, you can always look it up. So like, it's good to have some knowledge about Python, but don't worry, like you don't need to do a whole course about it. No, just learn a bit, and then with time you learn by doing. This is something. The other thing, and I'm also gonna upload some videos on YouTube that you guys can see, some courses that you guys can take on YouTube or other things to further study about it and things like that. But okay, so yeah, the only thing is that it can be very useful to learn it, and that's what we're going to talk about. So the possible applications of neural networks and machine learning in business, especially in finance. So okay, in finance, yeah, you have forecasts. But also you can use neural networks for sensitivity analysis. Okay, Dafa, he knows what sensitivity analysis is, if I'm mistaken, because we did this together. But Lung, do you know what sensitivity analysis is?
I don't have any idea about it.
Yeah, so the thing is, sometimes in finance, you have like a project, and then the project has like some future cash flows, and then you have many variables. So for instance, you have the demand, you have the costs per factory, you have, and in demand, you could have like a number of online customers or a number of normal customers. Costs can be like a fixed cost, raw materials, and so on. So you have many things that can change. That this we call variables. So variables come from variation; they can vary. Sensitivity analysis is simply saying like, okay, if for instance my fixed costs increase by 1,000 euros, how much this will affect my net present value? Like by how much my net present value will increase or decrease? In this case, probably decrease. To know this, you need to model the thing. But sometimes a project is too complex to model. Like, okay, we did like the simulation analysis and things like that for enterprise risk management, if you guys recall. But like we had a pretty easy model, or actually like maybe the task was very complex, but we did not create a very complex model for it. But sometimes like if you have a multinational and you have many subsidiaries and they are correlated to each other, and you have the market and you have the exchange rate and you have the financial markets, and you have many things that are correlated to each other, but sometimes they are not, and things like that, it becomes very difficult to model. And even if you try, your model gonna probably be a bad approximation. So here, what you can do is you can create a neural network for it if you have enough data. But let's say you have enough data, so your project has already started, or you have similar projects in the past, and then you just create a neural network with the data, and then what you do is you get your results, like your variables, your inputs, and the only thing that you change is the fixed costs. So this one here will change. So here you're gonna increase the fixed cost by 1,000. The other inputs are the same. The weights also, they are the same as you estimated with your training. And then you have your output with the NPV. And then you can just estimate what the difference would be with NPV. So this is like, okay, so first of all, do you understand now what sensitivity analysis is?
Yes.
And do you understand now how we could use neural networks for sensitivity analysis?
No, not that.
Okay, so essentially you have the neural net. Let's say you have trained your neural network, and your neural network now is very good to know what your net present value will be. So you just put the inputs, like, I don't know, like the number of customers, and also the exchange rate, like euro per dollar, and things like that. So you have your inputs, and your neural network is very good. It will give you the correct NPV. And then you have this neural network, right?
Yep.
So now what we're gonna do is you're gonna keep everything the same. So you're gonna have the same inputs. The only thing that you're gonna change is the fixed costs. You're gonna increase it by 1,000 euros. The only thing that will change. And then you just put these things here, and you just ask, hey, neural network, what is the NPV? And then NPV will be, like, let's say it will decrease by 100 euros. If you don't know how the neural network calculated, I mean, you kind of know with what we learned today, but exactly how we calculate, like the weights and things like that, I mean, maybe you could redo it, but sometimes neural networks get very, very big. Like with my research, I train neural networks with more than 1 million parameters. If you try to calculate 1 million parameters, you become crazy. And so the good thing about doing like that, sensitivity analysis, is that's very simple. We just give the number, it will do its own thing. It is very simple for you, but at the same time, you're being able to model a very complex thing. The bad thing is that they don't really know how it's done. And this is like a problem with neural networks. We call them black boxes. So because, like, okay, and then it comes a bit of my opinion. By the way, my PhD will probably be about this, about trying to make neural networks more interpretable, more explainable. And then it becomes a bit my opinion, but so it's a very new field. Okay, everybody agrees that neural networks are black boxes in the sense that humans cannot understand what is happening behind the scenes. So we understand that we give some input, you get some output, and we understand all the concepts. So like to literally know which feature is important and things like that. In theory, you know, if you get out the 1 million parameters or even 1 billion parameters and you look at them each time and try to make all the connections, in theory, it is possible. In practice, it is impossible for a human to do this. So then there are like ways to improve this, to try to get an understanding of what is happening. This started like not too long ago, but it is increasing a bit. But there's still one weakness of neural networks. That's why it is important for you guys So not use neural networks with everything. Neural networks should be used with complex tasks. So if you have something that is simple, try linear regression. If it works out very well, yeah, done. If it doesn't, go to the neural network. Because in finance and in business, especially in finance, if you do something, at some point you need to explain to your boss how you arrived to it. And if you just say to your boss, I trained this neural network, and then he gave me the output, even if the neural network is very good, which is usually the case, even if the results are much better than like a linear regression, which is often the case, your boss will prefer the linear regression. Or because your boss does not have enough knowledge about machine learning, or because your boss needs to explain this to shareholders that do not have enough knowledge about it, and they want to really understand everything because they are investing their money in the company. So even though they are not as smart as you are, they want to understand everything that you are doing. So they prefer that you do things that are like worse than they do things that are very good but that they don't understand, because they are afraid that you will manipulate them or do something dumb or anything like that. Do you guys understand this?
Yeah.
Okay, so coming back, so we have the forecast, we have sensitivity analysis, and also we have credit scoring. I would say that this right here is the thing that right now we are most using neural networks. Because yeah, with credit scoring, you don't, I mean, like, okay, in the academia and research, you do care about like which features are important and why they are important to know if a company will default or not. But if you are a bank, yeah, you don't give a fuck about it. You just don't want to lose your money. And here we are using already a lot. Like, you don't care how the program estimated. If it estimates correctly, you just want to know, and then you're gonna know if you're gonna lend money to this person or this company or not. Yeah, we are using already a lot for the scoring. Yeah, forecast sensitivity analysis. Where we also have like modeling things to understand the relationships is also possible. And there are many also other possible applications. By the way, I forgot to mention, today we focus a lot on neural networks regarding time series, regarding estimating values, so like linear regression, things like that. But there are also other ways of using neural networks. But the concept is the same. You have an objective, you want to minimize the error, and the structure is the same, as I just explained. So for instance, with ChatGPT, the objective is answering questions well. The cost or the loss function is the number of questions that it answers well. For the rest, it is the same thing that I just explained today. It is true that it uses another structure and things like that. It's a bit more advanced and so on. But the idea, the concept, there's no difference at all. No difference at all. Like the training, learning is the same, literally the same. So here with finance, for instance, you could think like, I don't know, like helping people like chatbots so that we can decrease costs and things like that. This is also something that machine learning is starting. Okay, any questions about or any ideas that you guys think like, hey, we could use neural networks for this in finance?
I don't know, like yeah, any predictive analysis, I guess.
Yeah.
Which I think the most interesting use case and a lot of use case in finance, because many I don't know, interesting finance jobs requires you to do financial modeling, different modelings, and I think this is one way you can do the modeling.
Yeah, and like most cases, neural networks are going to be the best way that you can possibly model something, because they are so flexible that no matter which model you compare to, they usually are the best ones. The problem is this one of the black box. Another problem, like for instance with credit scoring, is sometimes, okay, the neural network will simply decrease the error, right? But sometimes the neural network will learn things that are not true, or they might be true, but we don't want them to be true or to stay being true. For example, so you have like credit scoring, right? And well, I can speak about my country, so Brazil. So in Brazil, 50% of the population is black. But if you go to a favela, this number usually increases to 70%. So there is a concentration of black people in poverty due to slavery and many other problems in our society. But so you can say, and you can prove statistically, that there is a correlation between being black in Brazil and being poor. But if you guys remember from statistics, correlation does not mean causation. So it does not mean that if you are black, you are poor, or if you are poor, you are black. Like that one thing causes the other. No, it just means that there is a correlation, and it's because there is some social problems and things like that. But there is this correlation. Up until nowadays, this exists. If you train your neural network with credit scoring, there is a problem with your sample, like because of society. Namely, the problem is most poor people will be black, and it's well known that most poor people will default, or like most people that default are poor, better said. So the neural network doesn't really have any knowledge. So then for the neural network, black, or like your skin color, is just another parameter, like your income or your education level. It doesn't really care about it. It just thinks like, okay, these are parameters, like features, and I just want to minimize the error. This is it. So what can happen, and what happens, is that the neural networks learns that if you are black, you have a higher probability of defaulting, of not paying back your loan. And then banks will decrease their loans to black people, and then the sample that they will have for the training set of black people will decrease, which you will like, and then once again we still have this problem of most poor people are black in Brazil. So then this bias that we created, that is true because of correlation nowadays, will be reinforced for the neural network. So the neural network will continue thinking that black people are bad payers, and then black people will not get their loans, so that they will stay poor, and then like it's a vicious cycle. This is a problem of neural networks. It's not because of the neural network itself. The neural network works perfectly, but it's just our society is not perfect. Well, we strive for perfection. So for instance, we don't want that black people or minorities are that they are discriminated and things like that. But they are currently are. So if you train a neural network nowadays, the neural network will learn these discriminations, and will think that these discriminations are the way that we should continue living. Like that is the way that the world is, which is not true. Like we don't want to this. So this is a problem, and this is a big problem of neural networks. Like there are ways, and there is also a research field called AI ethics, which tries to which tries to handle this problem. For instance, here with the black people in the credit score, but there are many other possibilities. One example is that, like, so once again, as I said, like, most poor people are black in Brazil, and most poor people default. So you have this issue. One thing that you could do is you could create synthetic data. So everything with synthetic means like non-natural, not real. So you're going to create false data, but it is still representative, so it's still good data. So essentially, you're just going to make like more or less a copy of real people, but instead of having black, you're going to have white. Or it could be the opposite, of course. If you have too many white people in a certain group, you're going to create more black people to try to equilibrate this. Another possibility is that you're gonna say, like, okay, you have your error, like your error function, right? But the error that you have here is actually the sum of 0.8 times your error for black people plus 0.2 times your error for white people. And you will do this because, well, there are more black people the default in your sample, but you know that it's not because they're black, it's because of the social thing, but you don't care about it. Like, you want to really know if someone will default or not based on their characteristics. And you don't want to be racist. You hope that in the future this will change. So then by doing this, your error for black people will count more. So our neural network will not learn that black people, that being black, will increase your chance of default. And there are other possibilities of doing this, of being more ethical, more responsible with the use of AI. But these two things are very important to know. The AIs are very good, very powerful, but there is this problem of interpretability of the black box, and there is this problem of bias, not because of the neural network, but because of our world or the data that you have. For example, another example is like, this actually happened. So you have something called survivorship bias. You guys know this? So during the Second World War, the English people, they were losing many people that were like, what is it called? Many pilots. They were using many pilots during the Second World War. And then what they wanted to do is, like, they wanted to make their airplanes better by reinforcing the places that were being shot. So if the place would be shot and that the plane would go down, then the person would die. But if you reinforce these parts, that the plane will not go down, you will be able to resist more. So what they did is, every time that the plane will come back from the war, they will analyze the plane and will reinforce in the places that the plane got most shots. Does anyone see a problem with this?
Yeah, this is the classic example of the survivorship bias, where you only check the survivors because the one that got hit in the cockpit probably just dies straight away.
Yeah. Yeah. So you are reinforcing the parts that are already good instead of reinforcing the parts that are bad, because you are only looking at the good planes, the ones that came back. And this also happens here. So, for example, well, I cannot think of an example right now.
Yeah, I think also like successful people, right? Like, you only look into successful people, like, okay, and then you say, oh, this guy did this, but then you don't see the people that also do it, but it's not successful.
Yeah, for example, with this thing here, that, like, we're predicting the future income based on the number of hours studied. Let's say that we get this data set from an university, like let's make the example more extreme. we get this data set from Harvard. So the people that study in Harvard. Yeah, I mean, if you get this data set from Harvard, first of all, the number of hours is going to be like quite high already. And secondly, the income are going to be quite high. So your model going to be very good. They're going to be very good for people that study in Harvard or in prestigious universities. What about the other people? So sometimes the sample is very important. Okay. We could stay here forever, talk about neural networks. But I don't think there is anything that we can learn right now that we have time to. I will post these drawings that I did during the class today, and we also will have the recording, and we're also going to post it, and I will also post the courses that I recommend watch on YouTube and things like that. But also you can always look by yourself for new courses. Yeah, is also good. You can always ask me if you have any questions, things like that. I'm always open to help. And not only me, but like the community, the AI community there, and also the computer science community. So people that work with computer coding, they are very, very friendly and helpful. Yeah, Daf already knows about it, but Lam probably doesn't know. There is a website called Stack Overflow. It's a website where you put your questions and then people answer it. Or people, you just look at questions that were asked one day and then just see the answer. And like, really, like, it doesn't matter, yeah, where you are or where who you are. If you put your question there, probably within one day you're gonna have an answer, even if your question is very stupid. So really, like, don't be afraid of asking. Where like everybody in this community are very friendly, like really strikes me in a positive way. So yeah, so this is it. Now regarding careers and things like that, first of all, I would recommend learning Python. Even if you think like this neural network is not for me, but knowing how to use Python can be very good. First of all, because of it will be good in your CV. Secondly, if you know how to use Python, you can automate many things in your work. So if you have a job and you're probably going to stay there for 10 years, if you know Python, if you learn Python, and then you try to automate your job, yeah, you can make your life quite easy. I know teachers at home that used to, like, for instance, they used to classify study abroad programs, and they used to do this by hand, just looking and writing down things like that. It would take them a whole day, whole work day, so 8 hours. And I talked with a teacher from the HAN, and he used artificial intelligence. He got like a pre-trained model, so from the internet, and this is also something good. You can always get pre-trained models from the internet, so you don't need to train every time. He got it from the internet, he used it. It took like 10 minutes to do a 8-hour day work. And then he just had the free day. And while his colleagues were just using the whole day to do this. So, like, if you are creative, and trust me, when you start to feel the pain of doing repetitive and annoying work, you will start having this creativity, or actually this ambition to be creative to solve this problem. You will find a solution, and probably by using Python or any language that can automate. So I would really recommend this, and also with machine learning neural networks, it's difficult to say. If it will be like the future, like everybody right now is thinking like, yeah, everybody, like, we should use neural network and things like that because of ChatGPT. It's a big hype right now. I personally think that this will continue and it will become part of our society, like it was the case with, for instance, okay, maybe we're not gonna be like Excel or Microsoft that everybody gonna use it, because you need to understand some complex things like I just explained to you guys. But it will be part of our daily life, as already is with ChatGPT and other things. And if you know how it works and know how to code a bit, yeah, I'm pretty sure they're gonna get a good job in the future. Because right now, we already don't have enough AI engineers. So if you study a bit, you can easily get it. And yeah, I mean, if you also know how to use it for finance, you will be able to model things much better than everybody else. The only issues is the black box and the AI ethics, but we are, researchers, including myself, are working on it to try to improve it. And if it works out, it can be a game changer, a big game changer. And then we are the first, like neural networks are quite old, by the way, but they come back from the 80s. But back then the computers were not good enough to be fast enough to do this. So they were forgotten for a bit, and then they came back in 2006, 9, something like that. And now they are big hype. And so I believe that they will continue to be big hype, and they will continue to increase, like their uses and their importance. But we are the first generation to really use it daily, and the older generation is still not like that. So this could also be a competitive advantage of yours when applying for a job. Maybe you don't have enough experience, but hey, you know how to use AI, and you can even already give some ideas to the people they're hiring. How you want to implement AI, they're gonna be like, fascinated, and they're really gonna want you. So yeah, I would recommend learning a bit about it. Okay, so this is it. Any final questions then? I don't think so, right?
No, thank you.
Okay. I'm going to stop the recording then. Okay, so thank you for your